Start now. So where did we leave off? Well, last class was probably overwhelming for many of you, because if you're anything like me, it was very overwhelming for me when I was a student. But you always got to think, if O'Grady learned it, then you can learn it. That's sort of the way I would encourage you to think about it. Okay, so what did we do? Well, we did the following last class. So last class, we defined what a Riemann sum was. Let me remind you what it looks like. It's this, we use this sort of scary notation. So I am not going to write this all down again, but basically what this is shorthand for is this is shorthand for the following sum. So this Greek letter sigma, what it does is it tells us to add up these terms. And it takes some practice getting used to this thing. So that is what a Riemann sum looks like. And what we did is we talked about three very particular useful ones. So let's make sure you're aware of at least their names. So we talked about left, right, and middle. So we gave you some examples on how you can work with them, and we'll give you some homework to practice that. But it's important that, you know, the intuitive ideas behind what we're going to start doing and what we're going to continue to do in Calculus 2, the intuitive ideas comes back to understanding what this Riemann sum is doing. The motivation is we're trying to understand the size of a curved region. And so what this Riemann sum does is it says, let's try to approximate it using a much simpler shape, which is a rectangle. So you might, again, want to always think that this f evaluated at something, these are all the heights of our rectangles. And then this delta x over here, that is the width of each rectangle. So as I mentioned last class, I can't emphasize enough how important it is for you to study examples where n is 4, because you can easily draw 4 rectangles. If you want to learn this, attack n equals 4 on the interval 0 to 1. That's the best way to learn it. You study that simple scenario. Does anybody have any questions about this? Okay, the next thing I would say then is,
I have one question.
Yes, what's up?
So you remember last class we did the rectangle thing where with a quarter outside and then a quarter inside?
What do you mean a quarter outside?
Like 1/4 into 0 plus 1/4 plus 2.
Oh, yeah, okay, yeah.
Yeah. So does it mean that 1/4 and the 1/4 inside, they make a square?
Say that again. I'm not quite sure what you mean.
So there's a 1/4 outside, which you say that's the height.
No, the 1/4 are not the heights. The 1/4 are the widths.
And then the outside one is the height, right? The delta x is the height.
No, the f evaluated at the inputs, those are the heights.
And then the delta x is the width.
Say that again?
The delta x is the width, right?
That's correct, yep.
Yeah, so the 1/4, there was one outside which makes it delta x, and then there's a 1/4 inside which makes it f evaluated to x.
Yeah, the reason the 1/4 showed up inside is because that was our partition. Those were our x1, x2.
Okay.
So if you look at that example, you know, it's only a coincidence in this particular problem because we are taking 0 to 1. Anytime you're going from 0 to 1, your delta x is going to be, of course, outside of the sum because you're factoring it out. But you should also think about the fact that when you're between 0 and 1, your partition is 0, 1/4, and then it's 2/4, 3/4, etc. And so that's why it seems to be a coincidence, but that's only going to be the case on 0, 1. If you went from like 1 to 5, if you wanted to go over that interval, you're not going to see the same pattern. You'll see a similar pattern, but it'll be different. So there is definitely a pattern that's going to show up, and we're going to show you what that pattern is today. But the pattern is similar but different depending on your function and what interval you're on. Does that make sense?
Yeah, it does.
Yeah. Okay. The other thing to keep about in your head is the area idea is only there for motivation. As I said in the past, these types of sums will show up in many different areas, not just talking about area. So the area idea is going to be a very specific example of a much bigger thing. So that's kind of where we want to evolve to today. And it's very similar what happens when we studied the derivative going back. How did we motivate the derivative? We motivated talking about this idea of the tangent line and this idea of how do we define velocity. And then once we learned that there's this thing called the derivative, we learned it can do much, much more than just describe tangent lines. And it can do much, much more than just give us a physical or a mathematical way of quantifying velocity or defining velocity, I should say. So these Riemann sums are motivated from area. But what we're going to find out is that they're much bigger than just area. They're going to be able to answer many, many more questions. And some of you will get to see a lot of this in your education, depending on what your major is.
So does it mean like this is for the area, right? The one you told us.
Well, no. Again, I am motivating this through area. You guys have to understand what we're trying to do here. We're not saying that the only thing we're interested in is area. We are motivating a tool by showing you this tool, which we're going to call integration, if you've ever heard of it.
Yeah. So
motivation,
the format won't change, right? The format won't change. If you use it in another area, like another aspect, the format won't change, right? It will still be the same.
No, the formula never changes. It's just how we're going to interpret it. Okay. Sometimes we'll interpret it as area. Other times we'll interpret it as volume. Other times we might interpret it as just some mathematical thing. Some of you will take more classes and you'll interpret it as things like work done. If you've ever studied physics, you might interpret it as a way of determining how something accumulates. There's lots and lots and lots of applications of integration. We are just motivating it with one of its applications, which is area. And the reason for that is it's intuitive and it's also the classical motivation. That's what humans were worried about hundreds and thousands of years ago. How do we assign area to curved regions? Okay, so that's where we head today. So good stuff. So let's sort of reset that and set the stage. So Riemann sums turn out to be useful for many applications, not just area. So that's what I'm trying to say. And so because of this, we make a general definition for a new sort of procedure. And for some of you who are in the know, this procedure is called integration. So before we make this definition, we need to go back actually 2 classes and think about our example. So let me change. I like changing colors. Let me stretch. So if you go back, I believe it was 2. So we did the original example of y equals x squared on 0, 1. So here's what we actually showed. Now, we didn't say it in this language, but now with the language we talked about on Tuesday, what we showed is so as n, which don't forget n is the number of rectangles, sort of grew and grew, the left and right Riemann sums, quote unquote, approached 1/3, which of course is 0.3333. So again, go back to our lecture, I believe it was from last Tuesday, and we drew these rectangles, which at the time I didn't tell you that one was the left and one was the right, but if you go back and investigate, you'll see that. And then we went and did like 4 rectangles, and then we did like 8, and then I went to the computer and we actually drew a little table that showed you that those left and right Riemann sums were both approaching 1/3. So this is sort of a generic layman's way of suggesting there's some limiting thing happening. And we are on calculus, and you guys know what a limit is now. So we can make the following definition, which I call the O'Grady definition. It differs slightly from what you'll find in the book, and it differs slightly from what you might find on the internet, but I am going to phrase it so that it makes sense for us and it is logically sound. Does anybody have a question about what I'm saying before we do it? Comment.
How do we select the range of numbers when you are doing the left, the right, and the middle?
How do you select it? Is that what you're asking?
Yeah.
Well, we showed you how to do that. You just chop the whatever it is into n equal points, or n equal intervals, excuse me. I mean, I have to give you an interval. I have to tell you 0 to 1 or -6 to 7. I have to tell you an interval. And then once you have your interval, you chop it up. You just break it into n equal pieces. Now, we're going to do examples of this coming up, but we've already done it. See, the way What makes this really difficult to learn is this is not something you learn by listening or watching. The only way this is going to make sense to you is if you actually suffer through the goriness of doing it on your own. You just don't learn this. You know, math is not a spectator sport. It's just not. Now, once you try and struggle, it's very helpful to watch me or somebody else do it. Uh, but when you're trying, if you're trying to piece these ideas in your head, if you're just, it's just really difficult to do that mentally. You have to really take out a sheet of paper and scribble out the details. That's really the only way it's ever going to make complete sense to you. With that said, we're going to make a definition, and then we're going to what we're going to do is we're going to do some examples. So here we go. So definition. If f of x is continuous on a comma b, then this limit exists. So this scary limit will exist. Now, this is not an elementary fact, but we are telling you this is true. So what do? We denote this number as the following. We write this elongated s. So this is some notation which will become more apparent why we chose it later on. But we denote this number by this. Now, you're going to have to remember what all these symbols mean. I can't keep writing them down. We've written them down a few times now. So this limit exists. We denote it with this elongated s. And we say, so we call this number the definite or Riemann integral of f on a comma b. So this is a very scary looking thing. And it's even more scary if you don't take the time to understand what each one of these symbols means. You will not understand this in 10 minutes. Just not happening. Most human beings will require quite an effort to understand this. As long as you accept the fact that you're normal, just like I am, it's going to take you some time to learn this. There are very few humans on the surface of this earth that can look at this and say, oh, makes sense. Okay, so let's talk about some of what these things mean. Let's, again, we've introduced a new symbol. So the symbol is an elongated S. Why would we choose S? Well, you might say, oh, because really the integral is this sum. Now it's an interesting type of sum. It's a limit of a sum. So it's in many ways, it's like an infinite sum. It's a very difficult to define, delicate sum. The numbers A and B are called the bounds. F is called the integrand. And this is called an integration or an integral symbol. Woo! So you recall the quote unquote dx is called a differential. We talked briefly about that before. Now, as we move along the next few classes, what's going to happen is you're going to start to see why these symbols are the symbols we choose. Why do we choose to write it like this? For example, on the right-hand side of this equation, you'll see this delta, which is like a triangle. It's the Greek letter delta. You might say, why is there a triangle delta here, but the letter D over here? And there's a few reasons that that's the case, but the symbols are there to sort of show you and keep, sort of always try to keep in the back of your mind what's really happening. What does this dx represent? Well, that represents that we're measuring how x changes. And on the right-hand side, we're measuring this x by taking these little subintervals and taking their widths. Does anybody have a question? So I would highly encourage that you read this section in your book or on the internet, and look at other definitions and see how they compare to this. Does anybody have a comment, question? We'll let this sit in. Now, as I said, this number can be interpreted as an area. So let's think about that. So if you want, what is an interpretation or an application of the integral? Well, let's make this very, very clear before we do anything. The first thing is area. When can we interpret this as area? Well, if f of x is greater than 0 or equal to 0 on a comma b, the integral determines the area under the curve and above the x-axis. So let's just draw a picture of that real quick. This is sort of what we've done before. So if I decide to draw some curve, which I'll use blue, as long as it's positive, so if this is my curve, and this is my integral from A to B, so if I just look at the area between these 2 points, she's over here. She's fine.
She just goes around.
So if I were to shade in this region, so this red region that I'm about to shade in, so that red region, my kid pooped. So let's, you know, what we want to say is we want to make a definition, as a matter of fact. So the area of the red region is equal to, by definition, this integral. Ricky, go up. Pick her up. Ricky, go. You gotta go. We got drama here. Does anybody have a question about this? Anybody going once? Ricky, do you have any questions?
Say hey.
Say hey. Ricky, say hey.
Hi.
Hi. Seriously, does anybody have any questions? All right, cool. So again, the integral determines the area under the curve and above the x-axis. Now, this interpretation only makes sense if we assume that the curve is above the x-axis. That's why we make this assumption. Notice I said if f of x is greater than 0. Now, what happens if we don't make that assumption? So the next application or interpretation is what we call net area. For general f of x, the integral represents net area. So what does that mean? Well, let's draw a picture, because a picture is a much better way of illustrating this than me writing words. So now we're assuming our function is not necessarily always positive. So perhaps our function has the following sort of graph. So let's make the following sort of generic example. Let's say that this is A over here, and let's say that this is B. So now what does the integral represent? Well, if we get out our red line here, what is the region I'm looking at? Well, the region I'm looking at is the following. Oh. So this sort of region makes sense to us intuitively. This is, we can build our rectangles. But if you built rectangles on this next part, what you would notice is their heights would be negative. So on this part, you would imagine we're subtracting away So what we'd like to think about is the following. Let me get a different color. You might think about this plate, this guy underneath, you might think of this as negative area. If that makes any sense. And of course you might think of, so let me shade it a little different like this. And so the net area then from A to B of this particular function, this is equal to the net area, which if you want, you could think of as the positive minus the negative. Or let me not write it like that, because that's actually probably more confusing. Let me be very more explicit. So the way you think about this is the above x-axis minus the below part. Okay, does anybody have a question? Okay, comments? All right, so that is sort of the two ways so far that we can interpret an integral. So the integral is just some mathematical procedure, and if you would like, you can use it to interpret size of two-dimensional regions, which we always call area. All right, so let's do an example. So before we actually compute some specific what we should do is we should discuss some patterns. As I've mentioned numerous times now, what's going to happen when we want to do these Riemann sums and take limits and integrate is we're going to recognize patterns. And in all those examples I did, not just last class, but last week, I told you, don't just go to a calculator and compute this, because if you do that, you're going to miss out on the patterns. And if you might be saying, what patterns is he talking about? Well, we're going to show you in a second. Some of them should look very familiar. One of the beautiful things about math is anytime that there are patterns, we can often find shortcuts. And that's going to be extremely useful right now. So let's look at some things that popped up and will pop up in the future. So consider this. Suppose I take the number 1 and I add it up 10 times. What is this? This is 1 plus 1 plus 1 plus, and then I'm going to do this. How many times am I going to add up 1? Well, if you understand this notation says we're going to add it up 10 times. So if you took the number 10 and added it up 10 times, you expect to get 10 times 1. That's basic arithmetic, or 10. If you don't believe me, go to your calculator and add up 1. Do 1 plus 1 plus 1 plus 1 plus 1. Hit the plus sign 10 times and tell me what you get. You're going to get 10. Let's do a similar one. Suppose I wanted to add up the number 3 12 times. Well, the shorthand for that is this, but this would be 3 plus 3 plus 3. 3. And of course, just like I said previously, this is, if you want, you could say 12 copies. And so the shorthand way of writing this is you write 12 times 3, or of course 36. So if you went to your calculator and you decided to add up 3 12 times, you'd get 36. So what we have is the following. In general, so if I have C and I have N are any numbers, or I shouldn't say any numbers. Well, I guess I can. We'll be context here. We have to assume that N is an integer. What can we say? Well, you can say that the sum of C, if you want to add C up N times, This would be C plus C plus C plus C n times. Well, that's just going to equal n times C. So this is something that as a person, it's just nice, whether you're studying calculus or not, to understand how to simplify patterns. So this is a pattern that I'm not saying you have to memorize, but it's something that it's not hard to memorize, first off. It's something you could memorize. Let's do one more that you should be well aware of, and then we'll list a couple more. And maybe you've seen some of these. I don't know. Some of you may have had an algebra class where you studied these patterns. So now we want to consider another pattern. Let's consider this guy. Let's now add up 1 plus 2 plus 3 plus 4. Instead of just doing a specific number and over again, let's just add up to 10. Now, what is this? Clearly, you can go to your calculator and figure this out, but that's not very instructive because that doesn't tell us how to answer the question if instead of 10, I had 100. So if I asked you to determine this bottom sum, unless you understand how to use a computer creatively, it would take you quite a while if you don't recognize a shortcut. Does anybody know the shortcut to this? Does anybody know the answer? So even if you know the answer, what's more interesting to me is how one might obtain the quote-unquote shortcut. So what are the sums? So here's a very cute and actually what I would consider useful strategy technique for you to study because it gives you a way of thinking about a problem. So many of us, particularly students of your generation, well, not all of you, not all, you guys aren't all the same age, but even people from around my age and younger, we're so conditioned to just go to a calculator anytime we need to compute numbers. Now, that's not necessarily the worst thing because computation is tedious, and we know that calculators and computers can compute quicker than we can, and they're also not going to make errors like you and I are. However, when we're solving some problems, it's not always useful to go directly to the computer because if we do that, then we miss out on what's hiding and what other new ideas we might learn. So what I'm going to do is I want to let s be the number I'm after. So this isn't an integral. This is the letter s. So I want s to equal 1 plus 2 plus 3 all the way out to 98 plus 99 plus 100. So I'm going to write this out. Now, what I'd like to do is I want to know, is there some shortcut to computing this? And so oftentimes a strategy is to look at something from multiple perspectives and then relate those perspectives. That is a strategy that works often in math and in science. And you've actually seen this strategy in different ways throughout your life. When you first were in middle school, when you're learning how to add fractions, the first thing you do is study fractions that have the same denominator, and then you graduate to different denominators, and you learn that the way to do it is to find this common denominator. And in order to find a common denominator, you take a number and you multiply it by 1. Only you don't write 1, you write some strategic version of 1, maybe 7 over 7 or 17 over 17. So you're viewing something from a different perspective so that you can manipulate it to work. What I'd like to do is do the same thing. What I'd like to do is I'd like to add s to itself, but I don't want to add it in the standard way. So I want to do 2s, which is s plus s. Now, I do not want to write it the way you might intuitively think about it. What I'm going to do is I'm going to write the first s like this, 1 plus 2 plus 3, all the way out to 98 plus 99 plus 100. And then I'm going to write the second s. I'm going to write it backwards or in the reverse order. So I'm going to write this as plus not 1 but 100. And then not 2 but 99. And then this is 98. And then this goes all the way down to 3, 2, and 1. Now, why would someone want to do that? Well, it likely wouldn't come to your mind first thing. But the beauty of this is what follows is look at this and notice how I wrote it. If I now add vertically, each one of those terms adds up to 101. So let's be very, very careful with how we do this. My left-hand side of my equation is 2s, but what's my right-hand side? It's 101 plus 101 plus 101 plus 98 and 3, 101, 99 and 2, 101, and then, of course, 101. So I'm going to add like this. It's perfectly legal to do this. You guys know that you can add in any order you'd like. That's called the commutative property. Does anybody have a comment or a question? Okay, so let's go to the next page and let's write down what we have. So here's what we conclude. We have 2 times s is equal to 101 plus 101 plus 101. Now, we know how many we have of these. We have 100 of them. So this means that we have 101 times 100, or our sum that we were after, s is equal to 101 times 100 over 2. Now, you might just say, oh, Grady, why didn't you just write that and could tell us what it is. I don't care what this number is right now. What I'm looking for is the bigger picture. I'm looking for a formula that's always going to work. And if you think about it hard enough, you'll realize that we discovered a very, very beautiful formula. We just discovered the following formula. Here's what we just discovered. We discovered that 1 plus 2 plus 3 all the way up to some number n, we just discovered that it's always equal to n plus 1 times n over 2. That's what we discovered. We just took something that had n terms in it to add up, and we showed that it can be computed by multiplying two things together and dividing by 2. Now, of course, as a skeptic, you might say, again, O'Grady, who cares? Computers could do this for us. That you're missing the point. Even for a computer, this is nice because a computer can compute it by adding all those numbers together. Say n was 1,000. What would a computer rather do? Add up 1,000 numbers, or would it rather multiply once and divide? What would you rather do? Add up 1,000 numbers or multiply once and divide? Does anybody have a question, comment, concern? All right. So what we'd like to do then is the following. I'm not going to go through this, but you could. You could also derive a formula for this creature. So instead of adding the numbers up, let's add up their squares. 1 squared plus 2 squared. We've seen this before, haven't we? Plus 3 squared. It turns out that this guy is equal to nothing more than n squared. Excuse me, it's not n squared. It's n times n plus 1 times 2n plus 1 over 6. And we are going to use this formula over and over and over again. Beautiful. So I would hope that you look at this screen and say, okay, I'm starting to see why O'Grady, in his weird ways, wasn't adding those things together last class in the class before. Because now we're going to have some shortcut to evaluate Riemann sums when n is large. Now you're going to, you could start to see how I got those numbers real quickly 2 classes ago. I was just using this formula. And not only that, we now have a very efficient way of doing some algebra so that we can take limits. And you're going to say, well, why do we want to take a limit? We'll go back to the beginning of this class. We defined this new thing called the integral and it is defined by a limit. So let's do some examples. Before we do that, though, does anybody have a question? Comment? Concerns? So let's get this happening then. All right, so here we go. Let's start with the guy we have worked on numerous times and we think we know the answer to. Now, I'm going to tell you what I would do, and you don't have to follow my advice. You can do whatever you'd like, but I think it's good to just pick a Riemann sum that is your favorite. Maybe your favorite is the left. Maybe your favorite's the right. Maybe your favorite is the midpoints. I don't care what Riemann sum you want. There's infinitely many you can choose, but you got to pick one and stick with it. I like to choose the right Riemann sum because it's the easiest one for me to remember. So here we go. So what is our delta x? Our delta x is 1 minus 0 over n. Notice I'm not using 4, I'm not using 8, I'm using n because that's the definition. This is 1 over n. Now, what are my x sub i's? Well, this is going to be challenging. So my x sub 1 is 1 over n. My x sub 2 is 2 over n. My x sub 3 is 3 over n. And this pattern continues. My x sub n minus 2 is n minus 2 over n. My x sub n minus 1 is n minus 1 over n. And then lastly, my last point is x sub n, which is n over n. Of course, we know that that is also equal to 1. Now, I told you this last class, and I told you this on Thursday, or excuse me, last Tuesday. The best way for you to see that is to draw a number line and break it into equal pieces. Now, in this case, the number line I am using is 0 to 1. So if you're struggling to see this, take 0, 1 and break it into equal pieces. Here's 4, and then here's 8. What would these numbers be? What would these increments be if I used 8? What would they be if I used 4? And hopefully you'll start to see the pattern. Again, you will not learn this in 10 minutes. Just won't. Ain't gonna happen. Okay. So what's next? Well, what is our integrand here? Well, our integrand is f of x equals x squared here's what we have. We have the integral from 0 to 1 of x squared dx is the following limit. It's the limit as n goes to infinity. The sum k goes from 1 to n of f of x sub k delta x. Now I am using, as I told you, I'm going to use the right Riemann sum because that's the easiest one for me to use. It's always in my head. So I'm going to make a note of that. That's what I like. I like the right Riemann sums. I don't care what you like. Pick whatever you like, as long as it's a legal one. A legal one, I should say. That is, it's an actual Riemann sum. Okay, so what am I going to do? Well, I could do this in two different ways. I can write this out. And what I'm going to do is I'm going to do it in compact form first, and then I'm going to write it out without this summation notation. I'd like you to see both, because sometimes our brains don't interpret it right away. So if I keep it in this sort of compact sigma notation, what is my x sub k? Now, if you go back to the previous page, you'll notice that the x sub k's are k over n. And your delta x is 1 over n. So again, where am I getting this k over n? Well, look at each one of these x subscript values. X sub 1, 1 over n. X sub 2, 2 over n. X sub 3, 3 over n. X sub 4, 4 over n. X sub 5, 5 over n. So in general, the kth term is k over n. Now, another thing you might be curious about is you might be saying, oh, Grady, what happened to that little asterisk you had, the superscript? Well, remember, that asterisk just meant I can pick any point. But I am picking a specific one. I'm picking the right endpoints. I'm using the right Riemann sum. Okay, now what is f? Well, f is the squared function. So if I apply that, this becomes the sum. 1 goes to n. What is k over n? Well, that's going to be k over n squared times 1 over n. So right now you might be confused and you're kind of like, oh my God, all these letters and symbols. Okay, that's natural. That's what happens. These symbols are very scary. But if we really think about what each one of these creatures means, we can make some headway here. So what I want to do is I want to remind you what this stuff means. So we're going to write it out now. Now, some of you won't have to write it out. Some of you will get this right away. Others won't. But what I'd like to do is I'd like to write out this sum so you can see what's really happening. So remember, what does this sum mean? Well, let's do that on the next page. So the sum says I start with k equals 1, and then I add it all up. So what this sum says I'm doing is I'm taking the following. I'm taking 1 over n squared plus 2 over n quantity squared plus 3 over n quantity squared. And I'm going all the way out to n over n quantity squared. And then I'm taking this and I'm multiplying it by 1 over n. Now, if you were thinking in SOBIT, this is sort of what you were alluding to at the beginning of class. This is just a sum times something. And so what I can do is I can do algebra. I can use the properties of arithmetic. I can factor things out. And so what I'm going to do is I'm just going to rewrite this. I'm going to notice that every single term has an n squared in the denominator. And I also have a 1 over n way out here. So I can rewrite this as 1 over n cubed. And then what's left inside is 1 squared plus 2 squared plus 3 squared. And just like I did last week and I did on Tuesday, I'm writing it out like this. And the reason I'm going to do this is because I now have a very nice way of writing this ugly, scary sum. We just showed you it 5 or 10 minutes ago. And so whether you need to flip back a few pages or not, we know that this is n times n plus 1 times 2n plus 1 all over 6. Does anybody have a question? To this point, we're not done yet. Or as I like to say, it ain't over yet. Okay, now we need to compute a limit, so we're going to do some algebra first. So the first thing I want you to notice is I have some things that cancel right away. This n can cancel with that 3. And we can do a little bit of algebra. So I'm left with 1 over n squared times, what's upstairs? Well, this becomes 2n squared plus 3n plus 1 over 6. And now if I take this limit, this is the type of limit we discussed way back in chapter 2. If I look at this limit, I have a polynomial in the numerator. I have a polynomial in the denominator. Both of them are of degree 2, which means this limit is the leading coefficient upstairs divided by the leading coefficient downstairs, which simplifies to 1/3, as we expected. Woo! Wow. That was fun. Fun, 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 fun. Does anybody have a comment or a question?
I'm sorry, yeah, just one more time. How did we get 2/6?
Okay, so two things I need you to do is think back in chapter 2 when we discussed limits at infinity. Look at this thing over here. So there's two ways to do this. You can do it the shortcut way. So let's go to the next page and let's, what the heck? Why not just ask why? So that's a good question. So why 2/6? Well, let's look at the limit. What limit did we have? So we have the limit as 2n squared plus 3n plus 1 over 6n squared. That's the limit, correct? So one way, the shortcut way, is to say, okay, the polynomials match degrees. And so you take their leading coefficients, which are just 2 and 6. And in fact, that's the sort of shortcut trick you learned in a pre-calculus course, college algebra. You might remember you guys did horizontal asymptotes, and they taught you this trick on to see where the horizontal asymptotes were. They would say, look at the leading coefficients, 2 and 6. But then in calculus, we showed you a few months ago why that's the case. And the way to see it in its full detail is you factor some stuff out. Or if you want, you multiply by the appropriate thing. So I could write this, if I pull an n squared out upstairs, I'm left with 2 plus 3 over n plus 1 over n squared. And then if I pull the n squared out downstairs, I'm just left with 6. I guess I shouldn't write it like that. It's kind of silly to write it like that. And so what is the strategy that I'm trying to do? Well, here's what I'm trying to do, Thomas. I'm taking this and then I say, okay, this cancels and this cancels. So I'm getting rid of common factors. And so then the limit that I'm after is really just this. And now what happens as n goes to infinity? As n goes to infinity, I get 2 plus 0 plus 0 over 6, which is 2/6. And of course, that's just 1/3. So that is the long explanation for why it's 2/6. But you don't need to do that. I mean, that is the why. But if you understand what the limit is just by looking at it, then by all means, you should write down 2/6. Do you have any questions about that? Do I need to clarify anything? Anybody? We good?
Yeah.
All right. Okay, so there's a lot to sort of yeah, to soak in with this. This is not an easy example, and in particular, we're going to make these comments on the next page because it's important to know this. And so, some comments. First off, what did we do? We just verified that the integral from 0 to 1 of x squared dx, this guy is equal to 1/3. The next thing, and I'll ask you to maybe think about this, in a similar manner, you could show that the integral from 0 to b of x squared dx is equal to b over 3. Or excuse me, I should be more careful. B cubed over 3. For any b that's greater than 0. So if you want to have fun, try to do that. And the last comment I'll make is computing integrals by the definition is hard. And I'm going to put hard in quotations because that can mean lots of things. It's tedious, it's time consuming, it's conceptually challenging. As some of you know, there's going to be a real quick and short way of doing this, but the fact of the matter is that short and quick way doesn't always work. And so we have to have a definition that does always work. does anybody have a question or a comment that they'd like to sort of share or ask about before we go any further, or before we end, I should say? Okay, so if you guys don't have any questions, we'll end it there. I will look for a homework to get posted sometime later today. And we will do examples tomorrow. I'll be live at 10 o'clock as normal. I'm not going to do a 1 o'clock one unless you guys really want me to. It's really difficult to do that at home with kids and family and stuff. So I will definitely do an hour at 10 o'clock. Hopefully you can join. If you have any particular questions you want me to answer, send me an email and I'll do them at that time, or I can film it at another time and upload it. So please let me know if you have questions, and go check out the lectures. There's a link on Canvas and they're all on YouTube. So go check them out. If you have questions, please let me know. I'm going to start recording now.